Hello, ladies and gentlemen. Welcome to the IPv4 addressing video. So today we're going to be getting into the details. We're going to be talking about IP address. We're going to be talking about the structure, how a subnet mask works, and the information related to IPv4. So grab out your pens and your notebooks because today we're going to be learning some interesting things. Okay? So first thing, we're going to move on to the next slide. Let's go here. So core components of internet connections. We've got addressing. So addressing is IP address allocation and assignment. We've got naming, which is domain name and IP address. So there's like a link to them. You've got routing, which is relay packets from one network to another. Okay, so these are very core components. Now we're going to get into it. So the networking addressing scheme. So when you can see here, this is addressing. You've got layer 2, layer 3, layer 4. And through each one, you have different sort of attributes that stem from there. So we've got physical addressing, which is MAC related sort of stuff. We've got logical addressing, which is the IPv4 related stuff. And then the transport, which is port addressing, which uses the protocols UDP, TCP. And this is done through applications and service. This is end-to-end, node-to-node. Okay, so that's just a schematic of network addressing. Next slide. Hierarchy of addressing scheme. This is a different one. This is sort of saying you've got IANA, which is like the godfather that gives all the attributes to the networking stuff. It's quite complex, but you have to look it up. It's about regional stuff, but it's not really important in regards to this from my standpoint. But you might want to get into it and look into that. So we've got Internet Assigned Numbers or Authority, which is that stands for Regional Internet Registry, which is this one right here, and Local Internet Registry, which is this. So ISPs, which is like your internet service provider. And like, you have different things like Telstra, you've got AT&T in America, you got different sort of businesses that allocate addresses and all that stuff. All right. So understanding IPv4 addressing. So there's two methods to do it. I typically just prefer method one. To me, it just is more logical, just the way it's set up. But you can draw tables out. You can do all this if it's kind of tricky for you. But first we have binary arithmetic, right? So we're converting between binary and decimal and binary. This sounds confusing at the start, but it really isn't confusing. Now, binary is just on or off. That's all it means. Okay, so we have 0 and 1, which represents different things. So 1 being on and 0 being off. So when we want to convert 125 to a binary. So how would we do that? We'd have to look at this chart, which you don't have to look at a chart, but like you can make a chart. It makes it more visually easy. You could do it in your head, and I could probably do it in my head pretty quickly, but like you'd like to draw this out. So before we get into anything, all IP addresses, each octet, which is a sort of 8, so oc meaning 8, it operates in an 8 system. So there's going to be 8 sort of spaces here. Now, this will all make sense when we get into what an IP address looks like and so on, but this is how you would convert 125 to a binary. Okay, so we have 2 to the power 7, 2 to the power 6, 2 to the power 5, 1, blah, blah, blah. 1, 2, 3, 4, 5, 6, 7, 8. So 0 all the way to 7. And you'll look at what each of these equals. So 2 to the 0 is 1, 2 to the 1 is 2, all the way to 2 to the power 7, which is 1 to 8. So if we want to get a number in binary form that represents 125, we can't use 1 to 8 because that's bigger than 125. So we just start with this. We then add this, add this, add this, add this, and then we realize that if we add that, that's not going to equal that. So we turn that off and we turn this one on. And then if you do that math, on, which means plus everything that's on, it's going to equal 125. So it means these ones are off. Okay. So this is just converting, and this will be used when we use the subnet mask and that kind of stuff. All right. So it's basic. It's method 1. Method 2 is just this way where you divide all the numbers that you're dealing with. So you're dividing 125 by 2, and what's your remainder? You're doing that with the next one. And you do that with the next one, next one, next one, next one, next one. So basically, that's the setup you're given. So you can do that way. I prefer the other way, but other people might like this way more. I'm not going to get into this way. It's pretty simple. It's pretty logical. But the other way just works better in my head. You can choose. All right? So I think, well, let's take a look at this example. So we have the binary number, which is 11010011, and we want to convert this to decimal. So we count the total number of digits in the number, which is 8. We subtract 1 from the total. 8 minus 1 is 7. That number 7 is to the power of 2 to associate the highest number exponent for 2 in the number. Convert the exponential notation using all the digits as multipliers. So therefore, we have this number, this sort of binary number here, and it converts to 12864 plus 16 plus 2 plus 1, and that's going to be 211. Okay, so just pull out that chart again. It goes to the power of 7 and to the power of 6 to the power of 5 all the way down to 0. So always remember that your highest number can be 128, which is subtract the total of numbers in your octet minus 1, which is going to be 7, which is just always going to be 7. So like you wouldn't have to think about it, just know that it's always going to be 2 to the power of 7, which is equal to 128. And thankfully these exponential raised numbers don't go too high where it's at the point where you can't mentally calculate it. So you can mentally calculate 2 to the power of 7, or you could draw it out pretty quickly and be able to identify what it is, because you're just adding times 2 times 2, and luckily it's a base of 2, because 2 is an easy number to do. You're just adding times 2, right? If it was like 7 or something, it'd be a lot harder, but it's only 2, so it's kind of easy, so that's no worries. Now here we have binary, here we have the decimal, as you can see here. So the higher you go in terms of switching binary on, you get a higher number, okay? And it gives you the ability to like customize, which is what we're going to talk about later. We're going to talk about customizing how many hosts we want, how many networks we want, etc. And that's going to be done through the subnet mask, which is going to help us either supernet or subnet, which we'll get into that. But this is what it looks like. So if everything's off, right, in binary, you're going to have 0. If one thing's on, you're going to have 128. And obviously you can customize in here. Like maybe you could have this one on, which would be a different thing. 128 plus, so 64, 32, so 128 plus 16 would be a different number there, okay? So you can obviously, this is just a pyramid sort of example, going incrementally going up. So next one would be going down. And then this is just the mathematics behind it, which is really dead simple. So it's nothing hard for you guys to do. 128 plus 64 plus 32 plus 16 plus 8, plus 4 plus 2 plus 1. Now, understanding IPv4 addressing. So make my mic's working. It's good. All right, so IPv4 addressing is expressed in groups of 4 numbers. Now, each number, as we've discussed, the maximum you can get in each 4 group of the octet is going to be 255, sorry. And that's because when you switch the octet on all on, that's what your maximum number can equal, okay? And then we're going to go through why this is important later, but just know that 0 to 255, and it's a group of 4 numbers. So groups of numbers, sorry, and they're octets. So in this example, is this IPv4 address logical? 301 plus 256 plus 50 plus blah, blah, blah. The answer is no. This number is too big. Immediately wiped out. So it's not a logical address. They go up to this. Okay? Now, let's go to this one. So all devices connected to internet have a 32-bit IP address associated with them. Now, the reason it's 32-bit is because each octet is an 8-bit an 8-bit system. So, and there's 4 of them, so 4 times 8. So it's 16 plus 16, which is 32. And that makes sense. So it's a 32-bit IP address associated with each internet device. Oh, skipped a few there. So think of an IP address as a logical address, possibly temporary, while a 48-bit address on every NIC, which is a network interface card. If you went in the previous videos, that's in the playlist. That's the thing that connects the computers. That's the thing that literally either it's going to be connected to the motherboard or it's going to be like an external sort of adapter you have on different systems. But that's got a physical address to it, a permanent address, which is a MAC address. Okay? We went over that, so you can visit that, and you can go in other videos that are more in depth on it, because I didn't cover it in depth, but it's definitely there and available for you. Computers, networks, and routers use the 32-bit binary address, but a more readable form is the dotted decimal notation. which is obviously decimal, as we discussed, is numbers in terms of like 192 in the binary is like 1010, which is you're going to be on and off. Now, logical addresses are 32 bits, 4 bytes long. Each byte is represented as an octet, decimal number from 0 to 255, usually represented in the dotted decimal notation, example 172.24.208.192. That's a valid address you've got right there. Now, your address has two parts. This is something that is very important. You have your network portion, so the network ID section and the host ID section. Now, in this address, for example, we've got 172.24.00, which is your network portion. We've then got 208.192, which is your host ID portion. Now, this is going to tell you what host you're on, so what device this is, for example. And then it's also going to tell you how many potential hosts on the network are there. Well, it's going to tell you how many there are, but you don't know how many are being used per se. But it's going to tell you how much there's up to offer. So, for example, the 32-bit binary address. This is one right here, and this is what it looks like in decimal notation, okay? So that's pretty simple. I'm pretty sure most of you guys can calculate that. I'll just briefly go over it. So that's 128, because that's the first octet. You got 128 plus 16, 8, 4, 156. You got 8, 4, and 2. So 8, 4, 2, 12 plus 2 is 14, sorry. And then you got 1, 2, 4. So that's 7. All right, that's pretty simple. This one, you can do the math here. It's dead simple too. 128. I think they've actually made an error on this one. That should not equal that. Yeah. When I grabbed this online, that shouldn't equal that. So that should be. I'll just quickly pull it up so you can see here. Because when you do the maths on that, I just want to make sure right now. I'm going to sound stupid. 128 plus 64 is actually 192. So there's actually made an error on that. And then your second octet, which is going to be 128 plus 64 to 32, because that's the next octet. 64 is not used. 32, 16, 8. So that's actually going to be 163. Okay, so this is actually wrong, that one. Oh, wait. Well, there it is. Okay, I guess I had that there. I must have pasted that for some reason. But yeah, you see my point? Oh, okay. Yeah, righto. This is just saying the examples. Okay, PowerPoint doesn't. I didn't realize I thought it was going to do my slide, not do it incrementally. Anyway, understanding IPv4 addressing. When IPv4 addressing was originally created, there were. Okay, let's understand IPv4 addressing. So when IPv4 addressing was originally created, they were called classful addresses. Now that is each IP addressed on to a particular class, or a particular class address has a unique network. Okay, so I'll quickly go over what this means. There are basically 5 types of IP addresses. Okay, you have a class A, B, C, D, and E, which totals to 5. Now, convert the first octet of the IP address. So the first high order bit of the first octet is 0. So if your bit, let's just explain. Say you have the 8-octet address. If the first bit is 0, it's class A. Okay. If the second high order bit of the first octet is 1, 0, it's class B. If the third high order bit of the octet is 1, 1, 0, then it's class C. Now, what this looks like, it looks like this. So it's a range in the first few octets. So it really matters because it tells you what the class is, and different classes are used for different things. Okay. Now, class A, class B, class C. As we said, this one is going to be 128. So you've obviously got class B, which is 128, which means class A only spans to 1 to 128. Okay. Now the reason that is the case is because 127 is reserved, and you're going to jump here, and that's the reason it's done that. It's used for something else. I forgot to add it in this video, and I will try and add that in the next video. But it's a reserved address, and then obviously in this one you've got, you go to 191 to 192. So think of it as blocks that are reserved for different things. So it's got to do with the first octet of the IP address. Okay? Here is a chart to represent this. So if it's 0, 0, that means it's 1 to 126 because 2 to the power of 0 is 1. Now, the reason that's important is because that's going to tell you what your class is. Now, this one is, you can just pull out that chart and what it looks like. So binary to decimal. Now, what's this? This is 128. And then this one is 128 plus, 32 and the rest of them, which is 192, 191. And what this tells you is how many usable network addresses are in this. So in this example, you're going to have 2 to the power of 7, which is 128 addresses. In this example, you're going to have 16,384, which is 14 bits. So you're going to have 1, 2, 3, 4, 5, 6 plus 8, which is 14, because these two are reversed with the class. And these three are reversed with the class. And this one, it's because it depends on the class you're working with. I was deeply confused with this at the start, but once you understand this, it's not too difficult. But we have some more slides which will go into depth on this. So don't worry, you're going to understand. And then obviously, if you're dealing with something that has literally just the first octet reserved for the network, which is a class A, you're going to have, is it 16 plus 8 to the power of blah, blah, blah. Let me do the math on that real quick, just to make sure it equals that. So 2 to the power of, let's go 16, so 2 to the power of 24, which is going to equal 16,700,077 and 216. Okay, that was pretty poor reading for my part. But that's going to be -2 because you have the network and your broadcast addresses. So those are usable addresses in the network. That will be something we'll get into too, but don't worry. Then the next one, you've got the further, like class A, there's more host portion. Class B, oh no, sorry, class A, yeah, that's right. Class B, there's less. Class C, there's even less. So it depends on the octets, right? So class C, you're going to have 3 octets, which are dedicated to the network, and then 1, which is dedicated to the host, which is 2 to the power of 7, or 2 to the power of 8, sorry, because it's 8 that are going to be off. Okay, so that's important for you guys to remember. Now, don't get confused when we're talking about conversions. Like before, when we were talking about converting binary to decimal, we were using 2 to the power of 7. Okay, don't get confused about that. It's because the max. It sounds confusing, but when we look at this one, we're using 2 to the power of 8. That's because we can now work with all of the addresses, like all of the octet, in a way that. Yeah, I don't really have a way to explain it in a good way. There's probably other guys that can explain it really better than me because I'm just also new to this too. But when you're working with this stuff, because this is not right now, we're dealing with host and network and the classes. This isn't dealing with binary conversion. Okay, binary conversion is a different thing, but similar process in a sense in terms of calculating how many. Well, you're not calculating how many anything in the converting addresses from binary to decimal. You're just changing the sort of the language in which you read it with, and use 2 to the power of 7, 2 to the power of 6 to differentiate what's what, and so on and so forth. But you can go check that out. Just fast forward, go back and see how I did that. And this one, it's a different process. So it's going to sound confusing, but it shouldn't be that hard because just know that you can use 2 to the power of 8, 2 to the power of whatever, that goes down to 0 in that case. And that's going to tell you how many how many hosts you have on the network. So, in a class C network, your subnet mask is going to be, it's only going to allow, it's only going to allow, 1 octet for hosts. And I know this is very foreign, sounds foreign when I'm talking about subnet mask, but you'll understand. It's a lot of information at the start, but it gets kind of more chill. So addressing schema, 4 bytes, which is 32 bits, defining 3 fields. So class ID, network ID, and host ID. So this example, we have our class ID, we have our network ID, and our host ID. So if it's 128 here, this means that it's going to be a class B network. This is a class B network right here, okay? So you can use this chart over here and sort of differentiate what's what. But you can remember, you can also just remember this number arrangement that looks like up here. So this is saying your first, your last, your first, your last, your first, your last of each class. Now this, let's understand this section here. So this one is 0 and 1. So this is going to be 64. 64 lies in the addressing scheme of 0 to 128 or 0 to 126, which is class A. So class A, you have, you know, you have 7 potential bits for the network address because you used 1 for your class ID, meaning you're going to have 2 to the 7, which is networks. So it's 128 in terms of network potential minus 2. And the reason there's none of 127 is because that's reserved for something else. Okay? Think of it like that, but you can look into why later. So this one is 24 bits reserved for the hosts, which is also minus 2 because that's your network and broadcast. That's class A. Class B is 1, 0 to, is it 10 to 11? Oh no, it's 10 to the rest full, okay? So 131 was going to mean you have, what's that? 6 plus 8, which is going to be 14. So 14 bits to 14 bits. So 2 to the power, to the raised to the 14 bits, which is going to be 16,384. Then you have 16 bits over here, which is going to be different. And, as you will work with numbers that are raised, it adds a lot when you add numbers to this. So 15 to 16, 14 to 16, you're going from 16 to 65,000, which is crazy. Now, class C is 110, spanning to the rest are filled, right? So if you go here, 110, 110 right there, as you can see. And then the rest can be filled. Now, this goes 192. We've got this many bits reserved for the network, which is going to be a stack, which is that, and you got this bit for the host. I think you're getting the point here. It's sort of, the more you have hosts bits, you have more hosts. The less network bits you have, the less networks. And the more you have, the more networks. And then this is reserved for classes, so you can look at this and just determine what class it is. So you're not going to be just directly adding 8. So if you look at this, 8, 8 plus 8, you're not going to do that. You're going to do 8, 8 plus 1, 2, 3, 4, 5. Okay? Does that make sense? Some addresses are used for special services. Okay? So trailing zeros in the host ID represents the local network's address. So if it has 172.24.0.0, that means this is a network address. So this is the network address. This is what's going to be seen with routers and all that stuff when identifying a network. You have the trailing one in host ID used for the broadcast to all nodes in the local network, which is this. This is your highest possible host, I guess you could say, or highest possible number in terms of this address. When you're filling out the last 2 bits, the octets which represent hosts, to 255, which is on. Now that's reserved for the broadcast. Okay? So remember, the lowest potential you can is 0.0, which is for network addresses, and this is for broadcast addresses, which is 255, which is your full 8 octets switched on, which is 1, 1, 1, 1, 1. So that's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which is 255. Okay? Now, valid host addresses use only numbers 1 through 2, 5, 4. Now, as I said, that's reserved. What's in between 1 to 254? Kind of simple. So that should be too hard. Subnet mask addresses. So this one is a different address. This one is a different address. Now, what this means is if it's 255.0.0.0, it means this section is reserved. So the first octet is reserved for the network. The second section is reserved for host. Third section, host. Fourth section, host. Now, this one's different, as you can see here. and it tells you, which, representing 11111, 8 octets filled, and then this one's zeros and 00. So 127.0.0.1, and this is the one I was talking about, is called the loopback address, also referred as a local host. It is used to establish an IP connection to the same machine or computer being used by the end user. When you ping 127.0.0.1, immediately loopbacks to your own computer/machine to check whether the TCP protocol stack is properly installed or not, even when the computer is not connected to a network. Okay? So it's reserved and used for a purpose. That's why we don't use it. Today, IP addresses are considered classless addresses, which with clauses, classless addressing, class do not apply for a particular class of addresses. Instead, getting IP addresses from the internet/ISP. Most ISPs have already applied for a pool of IP addresses and leased them to their clients. Now, we've got a network mask determines which part of the address denotes the network portion, and also known as the subnet mask. It's a 32-bit number. 1 signifies network, 0 signifies host. Default subnet mask. So class A looks like this, class B looks like this, class C looks like this. And it's kind of like the other chart that we looked at, but 255.255.0.0.0 looks like that, as we've established, and so on and so forth. And they do tell you what class of addresses this is. Does that make sense? So that should all be chill. So masking is a process that extracts the addresses of a physical network from an IP address. Usually when a router forwards packets from one network to another, it uses this masking to identify if the packets belong to its network or not. So it extracts the addresses for the physical network from an IP address. How does QT router know whether a packet is destined for QT? So hint, 131.181.x.x, which is just unknown right now, is QT's class base. I'm using QT example. This is the university I go to. So the address, let's say the address block is that, and that represents this. So this is the network portion, and this knows. It will know where it's going. So I'll just go back to that if you didn't kind of catch my drift there. But the network portion is determined by those, which is this. So, yeah. It's a class B because the rest are reserved. The last 2 octets are reserved for your hosts. Okay? Now, it can be represented as a slash notation, the subnet mask, which is also known as the CIDR notation, so CIDR notation. Now, above example is the 16th network. So addresses and network prefix may then be shown in a compact manner, /16, opposed to literally printing out the subnet mask, which is going to take time if you're handwriting. So traditionally represented subnet mask, 255.255.0.0, and why would you want to write that? It's just saying, if you have .0.0, that's 8 plus 8, because you have 8 octets which are switched off, well, 16 in total, but in terms of each octet. And then you have 16 because it means it's representing which bit is reserved for the subnet mask. Does that make sense? So that's going to tell you if it's also a class A, class B, class C. The next video we're going to be exploring subnetting. Now, I know this video is probably a bit confusing to some people. If you have any questions, leave a comment. I will surely answer it. But if you didn't understand what I was saying clearly in this video, try look at Network Chuck. He's got some really good edited videos that can really help beginners. But if you're studying this in university, my level of understanding should be able to help you, and to some extent. But it's only going to get more complex from here, especially when we start using Cisco packet tracer and so on and so forth, which I will get into that later. But for now, we're going to learn the material. In the next video, we're going to be learning subnetting. So this one goes into more complex stuff, which is going to be sort of how do you sort of create networks for a specific task? Maybe you want to have a system, not a system, but maybe your boss has given you a task to assign addresses 100 here, 60 there, 30 here. How do you do that effectively? Okay, so that's sort of what we're going to be doing in the next video, and it's going to be a little bit confusing, but you need to understand this video I've done today to get to subnetting. So really simmer that over through your head. Keep learning the binary conversions. Learn how to identify, we'll briefly go back here. Learn how to identify your classes, your network portions, your host ID portions. And that's going to be helpful to understanding what class it is, if it's class A, class B, class C. That's going to help with like subnet masks and so on. But like I would say really just delve into converting stuff like this. So maybe do some online tests that give you like base sort of maybe a binary sort of address and then convert it. Like you could just chuck this in ChatGPT and say spit out some examples that I can practice on. Understand your sort of categories in class A, class B, class C. We don't really visit the other addresses, the other classes. Sorry, really get into that. Understand that boundary it's been set and why it's been set in terms of like why is it 1 and then 126, why is it 128 to 191. Look at this chart, understand that. Look at this, understand it's separating class ID, network ID, host ID. Go through these examples. We've done that, and yeah, like then you'll be ready for subnetting. Actually, like it's not that hard once you get it, but it does take a little bit of clicking and getting those brain cogs moving. So I would just really investigate that further before we move to subnetting. And yeah, let's go to